Hi. So I'm presenting some joint work with my current PhD supervisor on verifying equivalence of quantum circuits. Whoops. So I'm just going to start a bit about why we care about this problem, what exactly we're trying to do. Then we'll look at how the problem's been solved before and what's different about this technique. So one case where you might care about this is when you're dealing with maybe trying to do like something like a variational quantum algorithm or quantum machine learning in practice. So the idea is here we have some distribution we're trying to figure out, but like learn, but we don't really know what that distribution is. So we take some guess of what a solution might look like. So like an Ansatz circuit that has some parameters, you pick some parameters, compile it, then run it on hardware. You get some empirical histogram of what that distribution looks like. You can check if that is close to the distribution you're trying to learn by like some kind of an oracle. And you can keep doing this over and over again, refining the parameters until you get a satisfactory or a correct solution. But since we're kind of like running these circuits and compiling them over and over again, typically you might do some kind of a transpilation phase before you start plugging in angles. But since these are parameterized circuits, we're actually dealing with transpilation rules that deal with parameters now rather than just like specific gates. So for example, maybe I have a controlled Z rotation, and that might not be in my gate set, but we can compile it to a Z rotation and control it not in a standard way. The second case where these kinds of relations that I'm interested in come up is in super optimization. So we have some unoptimized quantum program. The standard approach for optimization roughly goes, you start with that, give it to an optimizer. It has some known optimizations that have been verified by hand by a human. It applies those rules until some conditions reached, and then you get some improved quantum algorithm. In super optimization, the optimizer both learns the optimization rules and then applies them. So as opposed to known optimization, we have some rules that have been proposed by the super optimizer, and then it uses those rules to optimize the circuit. The problem is these rules aren't actually validated by a human, so they have to be machine validated. And because you wouldn't want to like learn a different relation, let's say you had like, maybe you want to pull a Z rotation through a controller to cancel out. You wouldn't want to learn this relation for every possible angle. So you're actually trying to learn these parameterized rules that say, for example, for any angle I pick, I can always do this rewrite rule, and then I can instantiate it for the angles in the circuits I'm given. And the goal here is to ideally find like the most optimal implementation of the circuit, given whatever hardware gate set you have. So in both of these problems, what comes up is working with these parameterized relations about circuits. And when you want to like verify them automatically, this is harder than just verifying non-parameterized circuits. And that's I guess the idea kind of is when you have parameterized circuits, even if the matrices are huge, you could in principle just expand them out and check. In this parameterized setting, you're actually kind of dealing with analytic functions valued in matrices, so that's a lot harder to do. And just to make this a bit more formal, you have two circuits, you know what their semantics are, and you'd like to answer the question if for any choice of angles, maybe we have like k parameters now as opposed to this one, where the circuits always be equal. So that's the problem we're going to be looking at here. We're not the first people to look at this problem, though we do have some novelties to our work. So just to highlight that, we're going to start by looking at what's been done. So the earliest work on this goes back to 2019 by Wesley. He was kind of proposed an abstract framework for verifying parameterized quantum circuits based on Laurent polynomials and some category theory that went largely overlooked, but that is very related to what we're going to be doing, so I'll come back to this in a bit. A year later, Quartz was proposed. This was a super optimizer that basically does some transformations to the circuit until it becomes basically an SMT problem over like nonlinear real arithmetic, so then you can throw out a black box solver and it can try to check if they're equivalent. 2 years later, we got QC'C. This tool takes advantage of the analytic structure of these circuits to give a probabilistic approach to verifying it. One limitation of this is that it's assuming like an ideal sampling protocol where you can like sample an entire unit interval of angles, whereas on a real computer, you just have like some finite set you're sampling from. So it definitely works, but it would be nice if we could say something a bit more specific to how computers sample things, which came in the next week here, queso. And as we know, our quantum tools have to have queues, and we're starting to run into rules here, so I guess we're getting things like cheese. This technique instead kind of had the same idea that these entries tend to have some relations to polynomials, which we'll look at in a bit. So they use some techniques for like equivalence checking of polynomials, doing this probabilistically, and then lifting it to the circuits to get a probabilistic verification approach for the circuits. And some recent work that has just been brought to my attention after I submitted my abstract for this talk is there's also been some work on using a generalized version of tensor decision diagrams that allow for symbolic angles. I haven't had too much time to look at this, but it seems interesting. So I just wanted to point that out as well. But with this background work kind of outlined, we're going to take a bit of a closer look at what Miller-Bakewell actually did. This was kind of a methodology. In that sense, I mean, it's a framework that could be instantiated for many different kinds of quantum circuits, but it hasn't actually been implemented. Well, until here. Actually, this work, I wasn't actually aware of this framework until after I did all of this, but it's a very nice way to look at it, so I think it's worth pointing out. So the idea is we have k parameters in our circuit. You kind of like take a look at your gate set and try to find some way to describe the parameters of your rotations so that you have matrices over Laurent polynomials. So these are like regular polynomials, except you can have positive and negative powers now. And then you, for reasons I'll get to in a second, you want to know the degrees of these polynomials, but you also don't want to expand out the matrices because that could take a long time. So instead, you want to find an algorithm that can look at the circuit and get some upper bound on the degrees. And then once you know the degrees, in this work, what they did was they used results about polynomial interpolation to find some number of points you can plug into the circuits. And if they agree on those points, just by abstract things about polynomial interpolation, the Laurent polynomials have to be equal, and they're actually the same operators exactly. So in what I've done, we kind of thought about this in terms of root finding rather than polynomial interpolation. Mathematically, it's the exact same thing, but when you think of it in terms of root finding, you get some probabilistic variance as well, so that's nice. So now that we have the background work outlined, let's take a look at the kinds of quantum circuits we're actually interested in here. So we have like the standard kind of circuits you'd expect. We have some parameter-free gates. I won't worry too much about this in the talk, but they could be non-unitary as well, so like state preparation, post-selection, things like that. We have these rotation gates. This actually deserves a slide of its own, so I'll come back to what this means in a second. If you take any of the unitary gates or the rotations or the unitary parameter-free gates, you can apply arbitrary controls like in the computational basis. And I guess in principle, you could probably extend this to other bases of control, though we never thought about that while actually doing this work. And then you can either think of it as just taking the circuits over this, or if you like to be a bit more categorically inclined, we'll look at like the phi-monoidal category this generates. So we have empty wires, we can do parallel composition, put gates side by side, and we can also sequentially compose them. And this is kind of inductive, so you can do this with bigger and bigger circuits, the way you would expect. So when I say a rotation, what we actually mean is we're going to have some set H of Hermitian unitary matrices. We kind of think of these as like axes of rotation. So like in like, I guess the kind of rotations we see a lot, this might be like an X gate, a Y gate, or a Z gate. And then for each of these Hermitian unitaries, we're going to define a rotation that's basically just the exponential of that matrix, which is, sorry, this would be an equal sign there. That's like cos I plus I sine of H. It's like the rotations we're used to. But we also allow for multiple parameters, and you can take rational linear sums of those parameters. So this could be like 1/2 theta 1 plus phi theta 2. And then we also allow for like a constant term as well. We're going to assume it's a rational multiple of pi. I won't have too much time to talk about why, but like the technique works even if it's not a rational multiple of pi, but our implementation does rely on that. So I'm just going to put that assumption there. And there's some notation that's going to come up in a bit. If you give me a circuit, I'm going to write A of C for like the sequence of coefficients in the circuit. So basically you go through the circuit, find each rotation, look at the polynomial, and then you just, like we have A1 to AK here, so that's kind of like a vector. So this is just a list of all of those vectors. We'll see in a bit, though I won't have time to prove it, that this vector actually tells you an upper bound on the degree of the polynomial. So this is like the main thing we're using to do the analysis. And because it's just a sequence of coefficients that we get from the circuit, like you can find this really quickly, and all the calculations we do afterwards will also be pretty quick. So that's why we can find the degrees quite efficiently. So now that we have all of this context set up, let's just take a look at an example of how this technique works before I say more generally what it actually looks like. So we're going to go back to this controlled Z decomposition that we all know, but let's try to verify it. First, we'll do it the standard way we're probably used to seeing. We'll talk a bit about why that, not that it wouldn't necessarily work, but it would be hard to generalize, and then we'll see what this other technique looks like that we're proposing. Just for space on the slide, I'm going to do like a block decomposition here, but like if you expand out the right-hand side, you basically get a Z rotation by an angle, and then it's negative. And then in the bottom block, you have like the same thing, but one of them's conjugated by the X gates. So like that's going to, as we know, kind of like make the negative sign positive. But if you kind of work through the details, you get these exponential terms when you expand it out. We know how exponents work, so we can add the exponents, and then everything cancels out, and we get the identity in the top block. And then in the bottom block, if we expand it out, the same thing happens, but the X gate kind of flips things around. So we're adding the powers, so we get a Z gate back. And then if we put this back together, that's I direct sum the Z rotation, which is precisely the controlled gate we wanted. So they're equal. But the problem here is we have to do rewrites with these exponents here. And here I picked some nice matrices. Most of them are like diagonal. And the ones that aren't diagonal, that's permutation, so things work out nicely. But in general, you could have like really messy sums of powers of exponents. So some things could be done there, like there's some results about, I won't talk about this too much, but there's results from algebraic number theory, for example, that might help find rewriting rules for that. But it's definitely a hard thing to do. And as opposed to finding a rewriting approach that works for things like this, we wanted to find something a bit more general that doesn't rely on the specific structure of these gates. So alternative way of looking at this is we're going to do a change of variable here. So everywhere we had e to the negative I theta over 2, we're going to replace it with z. So that's going to give us some polynomials now. So if we look at the bottom right block, so this e to the I theta over 2, that's going to become like z to the power of negative 1. And then this will also be z to the power of negative 1. So then this term will be like z to the power of negative 2. If we look down here, this is z and this is z, so it's z squared. But then we don't really like having negative powers, so we can just pour this out. So we get these polynomial entries that have degree at most 4, and this negative power laying around there. That's kind of like a singularity that doesn't matter. It turns out we can ignore it, but I won't really prove that in this talk. Then if we look at the top block, we get the identity, then that's so everything lines out. We can lines up, we can pull up this negative power again, and we get more polynomials. So if we look at all of these polynomials, they have degree at most 4. And then if we move everything to the same side, it's just kind of like we're subtracting polynomials, so they still have degree at most 4. So we know that if they were equal, then if we have a polynomial that's degree at most 4, if we can show that if we can show that this is 0 on 5 points, then it has to be the 0 polynomial because the degree wouldn't make sense otherwise. We can't have 5 roots. So basically, if we pick 5 angles and just plug it in, we can see that they agree on all 5 angles. So then that means that they have to be the same because otherwise the degree of 4 wouldn't make sense. But the question kind of becomes, how does this generalize to multiple parameters? Because we know what to do with a single variable polynomial. Multivariable polynomials might be a bit trickier. So pretty much it comes down to these two theorems. I won't really read them out, but I kind of just want to point them out. The first one here is something called combinatorial Ansatz. It just kind of generalizes the root result. Whereas in a single variable polynomial, if you know its degree n, then it can't have, then it has at most, we know that bounds the number of roots. So the idea here is, here we can find the maximum degree of each of the variables, so like d1 to dk. And then if we pick then it can have if we pick any set of points, kind of like a lattice of points for the parameters, where this is size d1, d2 to dk, sorry, +1, so like we have to go one higher again. This is the same kind of thing where they can't be 0 on all of them, or the polynomial is identically 0. So it turns out that intrinsic generalizes the multivariable polynomials. It's just much harder to prove and not something we see very often. And then there's a second theorem that says that if we look at the total degree of the polynomial instead, then if we pick k points at random, both independently and uniformly, then the probability that the polynomial 0, if it wasn't a 0 polynomial, is bounded by divided by the number of points. So as we take more and more points, we can make that probability as small as we want. This was the same theorem used in Kazel, but the polynomials were arrived at a bit differently, so it's not the exact same result, but it's closely related. So I'm almost to the end. The idea is we wanted to go to Laurent polynomials and find the degrees for these root theorems, but we didn't actually want to expand out the matrices, so instead we proved that all of these circuits satisfy this predicate we call bound that gives us some idea of the maximum degree. It basically, okay, I can't make that all come up at once. It basically says that if for each variable we look at all of its coefficients, take the absolute values and add them together, then that's definitely an upper bound on the degree for that variable. And then if you look at the total degree of the polynomial for the probabilistic one, you can go through each of the coefficients and add them together. But it turns out, kind of like with negative and positive phases, they kind of interact in ways that cancel out. So it suffices to look at the positive terms and negative terms, and then take the biggest of both of them, and then the sum of all of those would be the bound the maximum degree. And then you just want this to have the same semantics, and we've implemented this. There's some other pieces that we won't have time to talk about, and as a proof of concept, even though the idea was to avoid matrices just to get this working, we've implemented this using matrices with cyclotomic entries. And we've also looked at how to deal with global linear phase, but that we won't have time to talk about. One caveat I kind of skipped over is these results assume all of your coefficients are actually integers, but you can just reparameterize the circuits to get it like that, so we implemented that too. You can find this on GitHub. So in future work, we'd like to look at sparsal representations and matrices like tensor decision diagrams. We know that for the way we're finding the bounds, they're tight in some sense, but if we could find more fine, like they're pretty coarse grained, so if we found like finer grained techniques for finding bounds, we could improve the efficiency of this. And there's also some techniques from classical program verification like symmetry reductions we'd like to look at to improve this. And we'd also like to generalize this to circuits with measurements, but that's all forthcoming. Thank you for listening.
Thanks for the talk. You mentioned you implemented this for like the cyclotomic gate sets. If you were to implement this for a parameterized gate set, what kind of challenges would there be? Maybe not just typing, but
so what we actually did was, so we've implemented this. So right now implementation actually handles all of the gates like in the standard library for OpenChasm, so that includes like X rotations, Z rotations, and Y rotations. The cyclotomic part is more like if we pick, because we can pick any angles we want, we can do this cleverly, so all of the rotations end up being cyclotomic. Like you could pick a weird parameter where it wouldn't be cyclotomic, but because we can pick the angles ourselves, we can avoid those cases. So does that answer your question, or were you asking something a bit different?
Oh, I was just asking if you were to implement this for, like, out of the box. Would this work? Would there be any like additional considerations you'd have to think about for implementing this for like these arbitrary single qubits, Z rotations or X rotations, or should it just?
We actually, that's what I'm saying. We actually have implemented it for that, but the idea is because we can pick the angles. When we do the analysis, we only look at the ones that give us cyclotomic entries, but it generalizes to all of the non-cyclotomic cases as well. Yeah. So the implementation already handles that. The computation just avoids having to deal with it.
Thanks.
No problem.
Hi, everyone.
Okay.
Near the beginning, you showed us the sort of list of coefficients that you said was going to be associated with each gate.
This one, or sorry? Oh, you mean back here, right?
Yeah. So I wasn't sure how you got the bound and the length of that list.
Okay. Do you mean like so if I'm assuming the circuit's already given, so like we know the length of the list is going to be bounded by the number of gates in the circuit, so you just kind of, it's like usually when you're doing this analysis, you assume like we're kind of like at least doing it linear in the number of gates, so like that we're kind of taking that to be n. So the length of this list would also be bounded by the number of gates. Is that the question you're asking, or?
That's half the question. The other
Okay.
half is how many coefficients you get per gate.
Oh, I see. So that was. Maybe I didn't write that. I condensed the slide. Yeah, so we're kind of making the same assumptions as in the Miller-Bakewell framework, where we're assuming a priori the number of parameters is a variable, but it's fixed. You don't have to, like, the way it's implemented is we just kind of analyze the circuits and infer what that number should be, but it's assumed to be fixed across all of the circuits. Yep.
Thanks. Okay, last question if there's one. No? Okay, quick.
Thanks. The low-end polynomials, do they tell you about something about like computability about some of these equivalence checking? Like, are there cases where you can look at the low-end polynomial and say, okay, this doesn't converge, or that these are the efficient cases?
So in the gate sets we're looking at, it really is actually Laurent polynomials as opposed to like Laurent series. So everything we're looking at is convergent. If we were looking at gate sets that you couldn't express with polynomials and you needed series, I'm not entirely sure what that would look like, but that's a good question.
Do you know much about the complexity of it?
I haven't thought about that case at all, so I can't really give any comments. But if you have any specific examples in mind, I'd be happy to talk about it later.
Yeah. Are they multivariate? Okay, I'll stop. Thanks.
Thanks, Scott.